Hello and welcome back to Aerospace and Mechanical Engineering Lab 2. Today we are going to talk about manufacturing, the second manufacturing lab, or VARTM. The objective is this lab is to study the flow through a porous media, since essentially just a glass fiber fabric, and the fluid that is moving through this porous media is the resin. Right? And then we are going to learn how to actually build a composite plate using the VARTM method. And your goal is to characterize the effective permeability of the glass fiber fabric. And eventually you have to do a statistical analysis on the permeability of this fabric. You have to make sure in the lab you have to capture a video of the flow that is passing through the fiber. Please make sure to watch the lab recording to learn how to do this yourself. So today we will introduce composites, what composites are. We will talk about the applications of composite materials, and we will talk about how to manufacture composite plates and everything else in general. And we will talk about flow through porous media. Composites are essentially material that are made from two or more constituent materials. A very widespread example, a very common composite material is wood. All of the wood we use everywhere is a composite material. It has fiber, it has resin that connects all of these fiber together. And we have been using this specific type of composite, for a long time. But nowadays, whenever you hear in mechanical engineering department or aerospace programs, whenever you hear the word composites, we are usually talking about fiber fabric like these preforms that are combined with a resin, and this combination has formed the fiber into a material that has a special use. So again, we start with a fiber and matrix. We create a lamina. Add all of this lamina together, and then we build structures. Why do we use composite materials? Composite materials in general are lighter than metals. They usually have higher specific stiffness and higher specific strength. And essentially, they are stronger because of extremely strong fibers that are aligned with the direction of the load. One thing that you have to keep in mind is that the strength of composites is directional. So a composite can be very strong in one direction and very weak in the other direction. You can see examples of the strength of composite and density and different types of composites compared to aluminum and steel in this table right here. Okay? And the composite materials are actually used widely in the industry. Like an aircraft, 50% of an aircraft is made out of composites because we want a strong light material in aircraft. Wind turbines, a huge part of wind turbines are made from composites. There are cars like BMW i3, this car, which is an electric car, that is completely made of composites. And it is very important to make electric cars out of composites because we specifically want lighter cars, lighter electric cars specifically. And it also have a lot of biomedical applications. You can see prosthetics made of composites, which essentially means that in all parts of engineering, you will see a composite material used to build things, everything in nature. But what are composites? Our composites, not woods specifically, our composites made out of. They are always made out of fibers. Then you have to connect these fibers together. You have to align them. You have to put them on, put them together in different shapes, different geometries, different patterns specifically. And these patterns these are called preforms. The patterns can have different shapes. We can have a biaxial wave, triaxial wave, we can have a knit, a lot of different patterns. And then whenever the pattern is made, a preform is made from the composite, what we are going to do is we are going to add resin to it. These resins can have two different types. We can have thermoplastics, or create two different types of composites. We can have thermoplastics or thermosets. Thermoplastics can be melted repeatedly and reshaped, but thermosets are essentially used. The resins are mostly thermosets. Essentially, whenever you use a liquid resin to create a composite material, once you shape it, once it is cured, you won't be able to melt it again and reshape it, which is essentially the thing the VARTM, the method the VARTM test uses, the VARTM manufacturing mode uses. You have a liquid resin, you add the epoxy with a hardener, you apply it to your fiber, and then just let it cure. Once cured, you won't be able to reshape it and change it. So again, thermosets and thermoplastics. Thermoplastics are solid at room temperature. They need heat to liquefy. They are remeltable and recyclable, and they are highly viscous at processing temperatures. On the other hand, thermosets are liquid at room temperature. They need heat and a catalyst, like the hardener we use, to start curing. And when it is cured, it is impossible to liquefy again. They usually have lower viscosity, so essentially they look more like a liquid at processing temperatures. Okay, so but how can we manufacture? What are the methods we can use to manufacture composite plates? There are different methods that we want to talk about. The first one we're going to talk about is a wet hand layup. The second one is a resin transfer molding. And the third one, which is our method of interest, is vacuum assisted resin transfer molding, or VARTM. Wet hand layup is very simple. You can see this solar car is made of composite. This is a solar car that was built when I was an undergraduate student. I was a part of this team, and our car actually participated in a solar car competition in Australia back in 2008, 2009. In that, a long time ago, 11, 12 years ago. Okay, so how does the wet hand layup work? Pretty simple. You have your mold. You start laying down the fibers, and then you add the resin, and you make sure the resin is completely covers your mold and your fiber uniformly at all parts using this roller. So pretty simple. You have a mold, you add your fiber on top of it, you make sure that the fiber takes the structure of the mold, and then you start adding your resin. You just have to let it cure. It will take some time to cure depending on your resin, depending on the hardener you're using for your resin, and it is a labor intensive process. You have to make sure the resin is spread uniformly. Okay. RTM process takes this a step further. So essentially everything is the same as before. You have to create your preform, you have to have a mold, but the difference is, instead of using a roller to make sure that the resin is spread uniformly, you are going to press it. You have to put another mold on top of your structure. Okay, so preform manufacturing, then layup and draping, then you close your mold, inject your resin, You should have outlets for the resin, the extra resin to go out of your system, and then you let it cure and demold it. VARTM takes it a bit further as well. So this whole process is going to be guided by creating a vacuum. You have your mold. For us, the mold is just a flat table because we are just going to create a plate and composite plates. You seal your preform, just essentially put a sealing plastic on top of it. You have an inlet for the resin. You have an outlet to the vacuum pump. Right? And then you start vacuuming your sealant, your sealed area, which is going to bring the resin in. Whenever the resin starts reaching the vacuum pump, your job is done, and you just have to let your composite cure. Plain simple. So different steps in a VARTM process is that you have to cut your preform. We are going to give you a roll of glass fiber, and just have to cut different layers, different numbers of layers, 4, 6, or 8, depending on your group, depending on the experiment you're doing. And then you have to stack your layers on top of each other. You have to add a distribution media, which essentially means that on top of your fiber, you have to add a distribution media. That is, in our lab, it's a green distribution media. The reason we have this is because we want to make sure that resin has enough room to come in and go out, right? If you don't have this, the sealant is going to actually close the inlet valve and the outlet valve, which essentially means that there won't be any flow through the media. So on top of your carbon fiber, glass fiber, whatever you have to add a distribution media. And then you create your sealant, your bagging, you vacuum your sealant. You make sure that you have to make sure that you have a perfect sealing, you have the perfect vacuum as much as possible. Then you impregnate your fiber by infusion, and eventually you have to demold. An example of the VARTM process. You see, this is your mold, and the green ones are the distribution media, and the black ones are your fibers. This is how it works. Okay, let me play it again. So your job is to record this movement of resin in the lab. Then you will be given tape measures. You will know where the resin is at all time, which essentially means that you have dx, dt. You know where the resin is, that's your delta x. You know what time it is, delta t. Based on this, you can find the velocity, and from the velocity, you can find the permeability of the fiber. Yep. Okay. You want to make sure that during the VARTM process, you don't leave a dry spot. And how we can make sure of this? We want to make sure that the distribution media covers all of the carbon fiber or the glass fiber, whatever you're using. The dry spots is going to create problems eventually in the strength of the material, because essentially you are going to have these air bubbles, and these are going to be the reason for deformity, for failure, for rupture in your media. So you want to make sure that everything is completely covered. How can we analyze this? How can we find the permeability? What is the method? We are going to use the Darcy's law. What does the Darcy law tell us? Darcy law tells us that the flow rate is equal to permeability in one direction multiplied by the cross-sectional area of your fiber divided by the viscosity of your fluid, your resin, in this scenario multiplied by the gradient of pressure, dP dx. Okay, we have to keep in mind that the permeability is not necessarily uniform throughout your cross section. It is directional, so we have to make sure that we create a one-dimensional scenario in the lab so we can use this formula. Otherwise, we have to use a matrix of permeability for this, and this Darcy's law is going to become a lot more complicated. So again, the goal is to create a one-dimensional flow. How can we make a one-dimensional flow? You have to create your preform in a way that is very long. The aspect ratio of your preform has to be as long as possible, so you can assume that the flow front is moving at the same velocity at all locations and is moving only in one direction. You are going to see more of this whenever you watch the lab video. Okay, so let's take it a step further. We have the Darcy's law again. We have to make sure that we create our carbon fiber in a way that the flow front, the resin front, is moving at the same time and is always at the same location. So you don't really essentially have a curved flow front. Very important. As uniform as possible. I'm sure in the lab you are going to get a curved front, but you want to reduce that curvature as much as possible. Okay, so for this velocity, for this scenario, we can introduce the flow front velocity, the concept of flow front velocity, which is capital letter U, is equals to U divided by the porosity of your system. So dx dt, the rate of change of location with respect to rate of change of time, is your velocity divided by the porosity of your system. What does porosity mean? Essentially, porosity is talking about the how connected your fibers are, how much room you have in between your fibers. Right? Think of a Swiss cheese. Swiss cheese has a lot of holes in it, which means that it is very porous. But the regular cream cheese doesn't really have any holes in it, means that it is not porous, at least to a naked eye. It is not porous. Okay, so let's take this formula a step further. We are going to have dx dt, which is your velocity. This is your front location. This is the time that has passed. The recordings are going to be very important in your analysis. It's going to be equal to negative permeability multiplied by delta P divided by delta X divided by viscosity multiplied by the porosity. Okay, this here we have assumed that the pressure changes linearly, so the derivative has become delta P. And at one point, at the inlet of your delta P, you have P1, whatever the pressure is, the atmospheric pressure essentially, because it is connected to the resin. As resin is pushed in using the atmospheric pressure, and P2 is vacuum, so your pressure is going to be zero pressure because the pressure of the vacuum is zero. So, and delta X is whatever the location is minus the starting port, which is where we put the start of the coordinate system, which means that the X at the starting point is zero. So to simplify this, we can say dx dt, the rate of change of location with respect to time, is equal to k divided by mu phi multiplied by the inlet pressure, again atmospheric pressure, 1 atmosphere, divided by x. We can take the integral of this derivative and come up with this formula, which essentially means that the location at any time to the power 2 is equals to 2 multiplied by the permeability multiplied by the atmospheric pressure divided by the viscosity multiplied by the porosity of your carbon fiber multiplied by the time. So this time and location is something you have to extract from your recording. P is the atmospheric pressure, K is the permeability, and the rest of the values, porosity and the viscosity, will be given to you in a table. at the end of this lecture notes. Okay. So what we want to see from you in the lab reports is, first of all, is this graph, which gives you the location at different time, and you have made a recording, meaning that you are going to know where each point is at each time. Do we need to have this many data points? No, you can have like 5, 6, 7, 8 data points, and using each data point and its corresponding time, you can find an effective permeability, which means that by just doing the test once and making like 10 measurements, 10 points extractions, you are going to calculate, you can calculate 10 effective permeabilities, okay, which will help you do that statistical analysis. Okay, so how do we calculate the effective porosity of this material? Since we have a distribution media and a fiber, that guiding media, and we are not interested in the effective permeability of the distribution media, we have to make sure that we understand that this plays a role, but it is not our interest. So this is present in the calculations, but this is not what we eventually want to calculate. Effective porosity of this combination is essentially just a weighted average. The porosity of the distribution media multiplied by the height of this distribution media multiplied by the porosity of the fiber multiplied by the height of the fiber. The height of the fiber will also be given to you, at least one layer of fiber. Then depending on the number of layers you are using, you just have to multiply it by the number of layers. The porosity of the fiber and the distribution media will also be given to you. And the effective height is essentially just these two heights added to each other. Okay? And it's also worth noting that if you have to calculate the porosity of the fiber yourself, you just have to calculate the volume of the fiber and subtract 1, or the total volume that is covered by the fiber, by the volume of the actual glass fibers. Do we need to do any of these calculations? Not really, but if you have to, well, I think the value is given to you. But if you have to do the calculations, you have the equation for it, number of layers, you have the density of the fabric, height of the fabric, and the cross-sectional area, which is this cross-section. So this line multiplied by whatever depth you have, like this height multiplied by width. Okay? And we can also do the same thing for the distribution media. Same equation, same everything. It's just done for a different material. Okay? And so using this equation that we have already found, you can find the effective permeability. Then you bring the effective permeability here to find the permeability of the fabric, the effective permeability of the fabric, for that matter. And this is the table that you will need for this analysis. The number of layers, it can be 6 or 8 or 4, depending on the number of groups you have in the lab. And we have the viscosity of the resin, we have the thickness of the all of the layers, you have to create the preform yourself, so you have to measure it in the lab yourself. The cross-sectional area is given to you of each layer of the fabric, and all of the information you need is also given to you. Okay, so we don't really give you the porosity of the fabric here. I'm looking at the table right now, which essentially means that you have to come here, calculate the fiber volume fraction, and then calculate the porosity of the fiber, and so on and so forth. So eventually this is your goal. This is what you want to calculate based on the equations we just discussed. That is it for today's theory lecture. Please let me know if you have any questions, and make sure to watch the lab recording.